History remembers the headlines. We find the bylines. This is the Unsung. 1957 was a year of shock and awe in physics. A cornerstone law of the universe, the law of parity conservation, had been found broken. The Nobel Prize in Physics was awarded with unprecedented speed to the two theorists who proposed it might be possible. Tsung-Dao, Ning. The headlines celebrated the triumph of a beautiful, daring idea. But an idea, in physics, is not a fact until an experiment makes it so. And the experiment that transformed their speculative what-if into a world-changing it is, was designed and executed by a third physicist, Chien-Shiung Wu. Her colleagues called her the First Lady of Physics and her experiment a masterpiece. Yet, when the highest honor was bestowed, her essential, grueling work in the laboratory was passed over. How was the experimentalist, who proved one of the century's greatest upsets in physics, written out of its most famous award? To understand this, you first have to understand who Chien-Shiung Wu was. She was already a force in physics long before 1957. Born in China, she emigrated to the United States for her PhD at Berkeley, quickly becoming a world expert on a type of radioactive process called beta decay. By the mid-1950s, she was a respected professor at Columbia University. Known for her relentless precision and a deep, almost intuitive understanding of how to design experiments that could wrestle secrets from the universe, her expertise was so renowned that when Li and Yang Hu were her former students were searching for someone to test their heretical idea, they knew only one person had the skill, the reputation, and the sheer grit to pull off what many considered an impossible measurement. Her power wasn't social or political, it was intellectual. She was the undisputed authority in the exact, difficult niche where their abstract theory needed to meet cold, hard reality. So, what was this pivotal contribution? It's known simply as the Wu experiment, and it was a feat of both experimental elegance and sheer The theory from Li and Yang was abstract. It suggested that if parity was violated, then in beta decay, the electrons emitted from a radioactive nucleus would have a preferred direction. Imagine a spinning top. If parity holds, it shouldn't matter if it's spinning clockwise or counterclockwise. Things happening around it should be symmetrical. Li and Yang proposed that maybe, at the subatomic level, the universe did care about the direction of spin. Now, here was the colossal problem. To see this effect, Wu needed to observe the decay of radioactive cobalt-60 nuclei. But to get a clear signal, all those tiny atomic nuclei had to be perfectly aligned, all spinning in the same direction. And to keep them from jiggling around randomly due to heat, they had to be cooled to a temperature near absolute zero. We're talking about just 1/100th of a degree above the coldest possible temperature in the universe. No one had ever managed to do this and measure beta decay at the same time. But Wu was undeterred. She formed a critical partnership with low-temperature physicists at the National Bureau of Standards who had the specialized equipment she needed. Her design was brilliant in its logic. First, she would align the nuclei. She placed a tiny crystal of cobalt-60 inside a powerful electromagnet at that unbelievably cold temperature of 0.01 Kelvin. This magnetic field acted like a drill sergeant, forcing all the nuclei to spin in formation. Second, she would detect the asymmetry. She positioned electron counters to measure how many electrons flew off in the same direction as the nuclear spin, versus how many flew off in the opposite direction. And third, she included the master stroke, the reverse check. In this critical control step, she reversed the magnetic field. This flipped the spin direction of all the cobalt nuclei. Now, if parity held, if the universe was truly ambidextrous, the electron counts should remain the same. The direction of spin shouldn't matter, but if parity was violated, the number of electrons flying off in one direction versus the other would also flip, mirroring the change in the nuclear spin. Over the Christmas holidays of 1956, while her Columbia colleagues were away, Wu and her team worked around the clock in the cold lab. In early January 1957, the data came in, and it was clear, stunning, and world-changing. The electrons were not flying off symmetrically. They showed a dramatic preference for one direction over the other. When the team reversed the magnetic field, the preference flipped right along with it. Parity was not just violated, it was maximally violated. The universe, at its most fundamental level, was not ambidextrous. It had an inherent handedness. Wu's experiment was the keystone. Without this empirical proof, Lin Yang's theory would have remained an interesting, but unproven, footnote in the history of physics. Wu had provided the fact. So why was she left out of the Nobel Prize? Wu's omission is a classic, painful case of systemic bias that has long plagued science, compounded by a few other crucial factors. First, there's the theorist's genius bias. Especially in physics, Nobel Prizes have historically favored the elegant, abstract theoretical leap over the messy, complex, and difficult experimental validation. The idea is often seen as the primary creative act, while the experiment is sometimes unfairly relegated to the role of mere confirmation. Then, there was the swift Nobel timeline. The prize was awarded in the very same year. The results were published at almost unheard-of speed. This left very little time for the scientific community to digest the results and appreciate the full, independent weight of Wu's experimental triumph. In the minds of the committee, the theory and the experiment were fused, with the theory taking precedence, and we cannot ignore the impact of gender and cultural bias. As a Chinese-born woman in a field utterly dominated by Western men, Wu faced a double barrier. While she was deeply respected by her immediate colleagues for her undeniable skill, she operated outside the informal old boys networks that have historically influenced recognition and awards. There's a subtle, gendered stereotype that often perceives meticulous, hands-on, experimental work as technical or craft, while theoretical work is seen as visionary. It's a false and damaging distinction, but it was prevalent. Finally, there was the nature of collaboration and the Nobel rules themselves. At the time, the prize could only be awarded to a maximum of 3 individuals, with Li and Yang as the undeniable theorists. Adding Wu would have raised complicated questions about excluding other key members of the low-temperature physics team from the National Bureau of Standards. These institutional constraints often create impossible choices, and in this case, the lead experimental architect was the one who was sidelined. Despite the Nobel snub, Chien-Shiung Wu's legacy is monumental. She went on to receive nearly every other major award in physics, including the prestigious Wolf Prize. She became the first female president of the American Physical Society and stands as a hero to generations of physicists, especially women and Chinese scientists, who saw in her a trailblazer of the highest order. Her experiment remains a fundamental pillar of the standard model of particle physics, the theory that describes all the known fundamental forces in particles. The modern correction to this history is not to diminish the work of Li and Yang, but to insist on telling the full story. The Parity revolution was a 3-legged stool, resting on Yang's insight, Li's mathematical formalism, and Wu's undeniable empirical proof. Take away any leg, and the stool collapses. Her story forces us to ask a critical question. How do we value the hands that test the ideas as much as the minds that conceive them? Wu's case is famous, but she isn't alone. Who are other experimentalists in history whose foundational work was overshadowed by theorists? Share their names and stories in the comments below. Let's give them the recognition they deserve. Thanks for watching. Subscribe to the Unsung to find more stories from the bylines of history.